In the last video, we spent a lot of time deriving the following expression for the Ising model. This is the specific Helmholtz free energy, specific because we've divided by n, which I've non-dimensionalized by dividing by kbTc. We also looked at the case where we've shifted this down so that at phi equals 0, the right-hand side should be 0 as well. And we found this effective expression for the case where we assumed phi to be 0 that we think applies near the critical point. All right, well, let's see what else we can say. In this video, we're going to try to take this as far as we possibly can using only the information that's on the board. But before we do that, I want to launch in and just be clear about what assumptions we've made. Oops. And I can really only think of three. The first is that we need F and F to both be analytic in the region that we're interested in. But when we looked at the van der Waals fluid in a previous lecture, we noticed that this is exactly the situation that we got. The Helmholtz free energy was well defined over its whole range of natural coordinates, but the Gibbs free energy did have non-analytic points. Secondly, we assumed that F of Tmn is equal to F of T minus Mn. For the Ising model, we saw that flipping all the spins upside down and then flipping our own heads upside down led to the same physical situation, which motivated the idea that these two things were the same. But we could have a similar symmetry in any kind of system that we might be interested in. And the third thing is we assumed basically the phase diagram, which we justified by saying that this is basically what numerics show us. And in particular, we know that M becomes non-zero at H equals 0 for T less than Tc. And if we made these three assumptions, we could get this expression basically for free. Since now this doesn't have anything to do with the Ising model, it's a good time to rename it. We say that the Landau free energy is exactly the one that I've written over there. Now you may also notice that between videos, I've made a change to our b of t function. I've made it into a constant. That's because we're interested in the region around the critical point, and we found that b of t was always constant, or was always positive, which means that near the critical point, the 0th order term will dominate. And so if we're only interested in that region, I'm allowed to change this into a positive constant b naught. So in fact, let me cross this out. B naught is greater than 0. Excellent. All right, one other thing. For the Ising model, phi represented the non-dimensional and also specific magnetization. But in general, if we have some parameter phi like this, we can write this expression down. So it makes sense to give phi a name, and that name is the order parameter. Why is it called the order parameter? Well, it's because in the ordered phase, that's the one where t is small, phi becomes non-zero at 0 applied field. But when we have t greater than Tc, phi is 0, and then we're in the disordered phase. So phi has non-zero value at h equals 0. And in fact, let me call phi's Legendre conjugate eta, just so we don't get confused. For the Ising case, this will just be a rescaling of h. Great. Phi has non-zero value at eta equals 0 for t less than Tc has, let me say, phi has 0 value at eta equals 0 for t greater than Tc. Excellent. Okay, now that we've fully abstracted this problem away from the Ising model, let's begin to find some of these quantities that I've written here on the left. The first one that we'd like to find is the solution at eta equals 0. So we know how to do that problem. We've done enough of these Legendre transforms by now. What we want to do is look to minimize over phi f. But notice that if we're only interested in finding the point phi, then we don't need to worry about this shift term. So we can just minimize the right-hand side of this expression. So we minimize a naught t minus tc times phi squared plus b naught phi to the fourth. Excellent. Now notice that because eta is equal to 0, I don't have to worry about my minus eta phi term here, although we will have to look at that in a moment. Excellent. Let's do it. What we get is that phi star solves 2a naught t minus tc times phi star plus 4b naught phi star cubed is equal to 0, since we're looking for a minimum. And we see that this has two solutions. Phi star equals 0 is an extremum, or phi star equals plus or minus the square root of, if we rearrange things a little bit, a naught tc minus t over 2b naught. Excellent. Now by our picture before, when t is greater than tc, this point phi equals 0 is a minimum. But when t is less than tc, this point is in fact a local maximum. So the local minima are these 2 points, which are in fact, they have the same value. So we can't resolve this point about the plus or minus sign, but that's all right. The main thing that we want, actually, is that phi at eta equals 0 is equal to 0 for t greater than tc, but phi of eta at eta equals 0, goes like the square root of tc minus t to the 1, or tc minus t to the 1/2 for t is less than tc. And this exponent is important. So I'm going to mark it down here in red and give it a name. This exponent is usually called in the literature beta. So we've just found that beta is equal to 1/2 for this Landau free energy with this symmetry. So notice that the symmetry that allowed us to neglect the odd terms is actually important here. It's coming into play. All right, I'm going to erase the board and we can start looking at our next quantity. Okay, our next quantity is the heat capacity at constant eta for eta equals 0. So let's remember that the heat capacity at constant eta is going to be the same as the heat capacity at constant h, since they're simply rescalings of each other. And the heat capacity at constant h is T times the derivative with respect to T of S, fixing H and N. Excellent. But we have one of our thermodynamic identities that says dF is equal to minus S dt plus H dm plus mu dn, where this mu is the chemical potential. And so partial T of F while fixing m and n is equal to minus s. So what that means is that C eta is equal to T times the partial with respect to T, so this outer one is going to be fixing H and N, and then another inner partial derivative with respect to T of F, but now fixing M and N with a minus sign. We can rewrite things in terms of little f by doing some substitution. So this says the following: C eta is equal to minus nkb t c, interesting, times t times the derivative with respect to t of the derivative with respect to t of little f. Fixing m and n is precisely the same as fixing phi. And then fixing h and n is precisely the same as fixing eta. All right, so now we have a good expression that we can actually work with. Awesome. Let's start trying to solve for this. So we'll go from the inside out. So first take the partial derivative with respect to t of little f while fixing phi. So partial t f while fixing phi is equal to, first we'll get first we will get f naught prime of t. Then we'll get a naught times phi squared. And that is it, since this term to first order does not depend on t. All right, the other thing is that f naught of t is going to be a function which also around tc can be Taylor expanded, but it's going to have a large 0th order term usually, and then first order terms which are smaller. So we can also neglect this term. Excellent. So near tc, we get that this is approximately equal to just a naught phi squared. All right. Next, we need to stick this back in here. So we get c eta is equal to minus n kb tc t times the partial derivative with respect to t of a naught phi squared, but a naught is a constant, so it can come out. And we just get phi squared and then eta. Good. But since we want to take a partial derivative of phi with respect to t while fixing eta, we should bring back our expression for phi. I'm going to drop the star here, but just reminder that it really is there. So this is 0 when t is greater than tc, and is either plus or minus, it doesn't matter because it's going into a square, a naught t minus, or tc minus t over 2b naught when t is less than tc. All right, so in either case, we will in fact get a constant. So partial t of phi squared, fixing eta, is then equal to 0 for t is greater than tc. Now if we square this and then take a derivative with respect to t, we'll get so we have a minus t here, so we get minus a naught over 2b naught in this case. All right, let's shove everything back in. So we get c eta is equal to minus a naught n kb tc times t times either 0 or minus a naught over 2b naught. And so if we want to just extract the behavior with respect to t when t is near tc of this thing, we can do that. And in particular, notice that c eta is just linear in t. And it doesn't have any sort of vanishing behavior when we take tc or t to be near tc. So we could say that this is equal to minus a naught n kb tc times, let's say tc squared times 0 minus a naught over 2b naught minus a naught n kb. So what I've done here, I've just split this into tc plus t minus tc. Okay, so then plus, or this minus sign here, t minus tc. times 0 minus a naught over 2b naught. So notice that I have two cases. In the first case, when t is greater than tc, c eta is just 0 to the level of approximation that we've made here. When t is less than tc, then we have this tc term dominating here. And so to the highest order, c eta is also constant. So c eta is constant when t is less than tc and we're approaching tc, and c eta is constant when we are greater than tc. In other words, c eta to the level of approximation that we've done here goes as t minus tc to the 0. Again, because we're neglecting this first order term in favor of this much larger 0th order term when we have t less than tc. So let's also extract this 0 exponent here, and this one is usually called alpha. So we have alpha is equal to 0. All right, let's erase the board and get on to our next object that we want to compute. Okay, the next thing on our agenda is to compute phi star of eta, but when we're at the critical point in terms of the temperature. So once again, we're going to look at this minimization problem. Now we're going to have everything down here, sorry. So a naught t minus tc phi squared plus b naught phi to the 4th, but now minus eta phi is equal to 0. Sorry, not equal to 0 yet. Jumping the gun here. But look at this. Because we're at t is equal to tc, this term just goes away. Okay, so now we can do the minimization problem to solve for phi star. So phi star solves for b naught phi star cubed minus eta is equal to 0. And in this case, we just have one triple solution for phi star, where phi star is equal to eta over 4b naught to the 1/3. Now, interestingly, by convention, the exponent that we're looking for here that tells us how phi star is related to eta is actually the 3 in the denominator here. Again, that's just a convention. So we say that phi star goes like eta to the 1/3. And I will imply that that is important. This one is usually called delta. So we have delta is equal to 3. Okay. Now, let's finally find the susceptibility called chi. And chi is defined to be, well, actually, different authors define it differently. Let me define it over here. So chi is defined to be the change in the order parameter phi as we change eta, its Legendre conjugate. Some authors would define this to be the magnetic susceptibility, which is to say partial m, partial h. But these are just related by a constant to each other, so I'm going to not worry about it anymore. And in particular, we want to look at this when eta equals 0, like we've been doing for many of the constants that we're calculating here. Okay, this is going to be hard to get, but we can actually get it by starting with this equation. So we had this maximization or minimization equation, but we neglected this term. Let's bring it back. So we'll get 2a naught t minus tc times phi. And this is phi star. I'm just going to ignore the star here for notational clarity. So plus 4b naught phi cubed minus eta is equal to 0. And immediately it seems like there's not very much that we can do with this, but in fact we can do something, which is take an eta derivative, and I should have been clear that this is a partial derivative fixing t. Okay, so let's do it. If we do that, we get 2a naught t minus tc, again t is fixed in this partial, times the partial with respect to eta of phi, we're fixing t, plus 12b naught phi squared times, again, the partial with respect to eta of phi while fixing t, minus 1 is equal to 0. And I can solve this for this object that I want. In particular, because these two terms share it. So I can just factor that derivative out and then move things around. What I find is that the partial of phi with respect to eta while fixing t is equal to 1 over 2a naught t minus tc plus 12b naught phi squared. Okay, now let's remember that the phi that's right here is really phi star. We want its square. And we're interested in the eta equals 0 case, but we've already solved for phi star squared at eta equals 0. Remember that this is 0 when t is greater than tc and is a naught times tc minus t over 2b naught when t is less than tc. So sticking that back in, we find that chi at eta equals 0 is equal to 1 over 2a naught t minus tc. And then the b naughts cancel. So we're only going to worry about this lower case. Okay, let me back up again. I don't know why this one is going so badly. So let me stick in our two solutions over here. So when t is greater than tc, notice that this phi star just goes away. So we get the chi at eta equals 0 is equal to 1 over 2a naught t minus tc. On the other hand, when t is less than tc, then we need to stick this into this equation. And let's do a little calculation over here. So 12b naught phi squared will be equal to, so again we have t less than tc here. That will equal 6 a naught times tc minus t. The b naughts, notice, have canceled, and we get a 6 here. But because we want to flip the signs here, we can actually think of this as minus 6, because then when we add it to what's up here, we'll get a minus 4. So here we'll get chi for eta equals 0 is equal to 1 over minus 4 a naught t minus tc. Excellent. Now in either case, we have that chi, in this case for eta equals 0, goes as t minus tc to the minus 1. And extracting just the 1 here without the minus sign is the usual way that this is given. So we get gamma is equal to 1. That's the name for that exponent. Okay, so this suite of exponents that we got, alpha, beta, gamma, and delta, were given to us just from a few very simple assumptions. Assumptions about symmetry, about analyticity of the Helmholtz free energy, and basically about the phase diagram itself. But this phase diagram will be pretty common to anything that has continuous phase transition with a critical point, and with a first order phase transition boundary below that critical point. In the next video, we'll see how this applies to the liquid-gas transition, and then make some statements about how these exponents are really pretty universal to systems that we see. Thank you so much for watching this one, and I'll see you in the next one.